we have the two functions f of x equals x cubed minus x squared minus 3, and g of x equals the square root of x plus 4. We want to calculate the function f of x plus g of x. And we could designate this as the function f plus g of x, a new function that we call f plus g, and it's defined in the obvious manner by adding the f of x and the g of x function. So that at every x, the value of f of x plus g of x is the value of x squared minus 3, which is the value of f of x, plus the square root of x plus 4, which is the value of g of x. So, it's a very obvious definition. F of x divided by g of x is, just as you would expect, the function where we divide the f of x function, x squared minus 3, divided by x plus 4. And we could call that function f over g of x. It's important to be able to recognize when you have a quotient of two functions. We'll see fairly soon that we have rules for taking derivatives. Now, I mentioned derivatives in the preceding, just in passing. You don't need to remember that definition. Just remember that they're really important. They're the central concept. They invoke, or they entail the rate of change of a function with respect to its variable. And it's very important to be able to find those rates of change for a lot of applications. So, when you have a quotient of two functions, there's a specific rule in terms of the derivatives of both functions, the derivative of this function and the derivative of this function, that allows you to determine the derivative, and you're not going to be able to do that unless you recognize that you have a quotient. So if you see this and don't know this and this, you should be able to figure this out. The top function you could call f of x, the bottom function you could call g of x, and that you have the quotient of those two functions. Now, the composite. And let me, we could also do the product. I didn't do the product, but that would be f of x times g of x, and you'd have quantity x squared minus 3 multiplied by the square root of x plus 4, and you got to be able to recognize that that's what you have when you see the function itself without knowing what the f and the g are. There's another rule for the product of two functions. To apply that, you have to be able to identify the product. Now, sums and quotients and products are easy to identify. Composites can be a little trickier. So let's do this composite. Now we're talking about f of g of x. And there is a notation for this also. It's the composite function is f circle g. Okay, so we define that. We could even say equal by definition. I'm not going to write that in. F circle g of x is f of g of x. Now, what is f of g of x? Well, f of x is x squared minus 3. We've replaced x by g of x, so we better replace the x here by g of x. And that's going to give us g of x quantity squared minus 3. Now, of course, we know that g of x is the square root of x plus 4, so we can do further substitution. G of x, substitute square root of x plus 4. So we have the square root of x plus 4 quantity squared minus 3. And that equals what? Well, that simply equals x plus 4, because the square of the square root of x plus 4 is x plus 4, minus 3, and that's equal to x plus 1. Now, I'll add one thing, just as kind of a bonus here. This function is only defined if x is greater than or equal to 4, because you have to have a non-negative quantity under here. So the domain of this function is restricted, and that restricts the domain of your whole composite. You can't do the composite that we indicate here if x is less than 4. Even though you could do x plus 1 if x is less than 4, you can't do g of x if x is less than 4. If x is less than negative 4. So even though you could do x plus 1 for x equals, say, 0, or even negative 1, you might not be able to do the square root of x plus 4 for that value. In this case you can, but in other cases it might be that you can't. If I'd have had a number here like minus 8, then I'd have had a minus, well, say minus 9, I'd have had a minus 5 here instead of a plus 1. And that doesn't make any sense at all. So forget I'm saying that. I'm confusing myself. So just the thing you want to take from that little bit of confusion is simply that x can't be less than negative 4. So if this had been a plus 9, then we'd have had x plus 13 here. And a number like negative 5 would work fine here, but it would not work here because negative 5 plus 4 is negative. Okay, so anything that you can't do g of x to, you can't do f of g of x to. Also, if g of x gives you a number that you can't put into f of x, then that's going to forbid you from using that value of x. That's going to restrict that value of x from the domain. Okay, well, let's move on. G of f of x is what? Okay, well, g of x is the square root of x plus 4. G of f of x is what? Well, we replaced x by f of x, so we replace x by f of x, and we get the square root of f of x plus 4. And that equals what? Well, f of x is x squared minus 3, so we can replace f of x by x squared minus 3, and then we have the plus 4. So now we have the quantity x squared minus 3 plus 4, and that simplifies to the square root of x squared plus 1. Now, so I don't confuse you and maybe even get confused myself, I'll simply say that there might be numbers here that won't work because they don't work in the function f of x. But of course, f of x is defined for every number, so the only restriction is going to be that x squared plus 1 has to be greater than or equal to 0, and it is because x squared is always positive. You're always going to get a number greater than 0. So for any number you want to put in here, f of x is going to work, and it's going to give you a number that works in the g of x function. So that even though, say, x equals negative 10 would not work in the g of x function, it works just fine in the g of f of x function, because you run that negative 10 through f of x is going to give you 97, and that number will go just fine into g of x. Okay, anyhow, that's how you write out the composite. Square root of x squared plus 1 is also, it turns out, the composite of what? Of g of x equals x squared plus 1 and f of x equals square root of x. So that f of g of x would go into the f of x function. G of x is x squared plus 1, so you'd have the g of x function here, you'd have the square root of g of x, you'd have the square root then of x squared plus 1. Okay? And these aren't the same functions that we used here. Okay? That's not these two functions. These two functions are a little bit different. But they still work. They still work to give you the square root of x squared plus 1. So when you're trying to find the composite that gives you a given function, you might have more than one choice. And this would be the choice that would naturally occur to you if you saw the square root of x squared plus 1. You would think, okay, we're taking the square root of something. What is it we're taking the square root of? It's x squared plus 1. So that we're going to do a composite that involves a square root function and the x squared plus 1 function. And that would then be these two functions here. Okay. Yeah, there's a little more, but we'll go on and maybe, well, let's see. Yeah, I kind of needed to check my time, but we got time to do this. We have f of x equals 2 times the quantity x minus 3. G of x equals x plus 6 over 2. And we want to know, does our composite f of g of x happen to equal x? If it does, then these two functions are called inverses, because whatever goes into this one, if we then feed that value into this one, it's going to give us our number back. Or if we do this one and get a number and feed it into this one, we get our original number. Let's just check that out. Let's say x equals 3. What's 2 times, let's say x equals 4. 2 times 4 minus 3 is 2 times 1, which is 2. Okay, if we put 2 into this function, we get 2 plus 6 over 2, that's 8 over 2, and that's 4, which is the number we started with. Any number we start with here, we evaluate f of x and plug that number into g of x, we get our original number back. Or if we start with g of x, okay, let's say x equals 4. G of x is going to be 4 plus 6, 10 divided by 2, which is going to be 5. If we put 5 in over here, we'd have 2 times 5 minus 3. 5 minus 3 is 2. 2 times 2 is 4. Again, if we put 4 into g of x and then plug that value into f of x, we get our original number back. So these are the functions that undo one another. Now, it proves nothing that we can do this for 4. We have to prove that we can do it for every number, but that's fairly easy to do. Now, I'll do it for f of g of x. F of g of x is, well, replace x by g of x, we get 2g of x minus 3, which is what we've got here. And then g of x is x plus 6 over 2, so we have 2 times x plus 6 over 2 minus 3. And you can simplify that yourself. You are going to end up with x. Now, you should also do g of f of x and show that that ends up with x. So what happens again is that any number you feed into f of x is going to give you a result. If you plug that number into g of x, it undoes that result and gets you back to the number you started with. Those are called inverse functions. And we'll notice up here that this function, which gives you x plus 1, came pretty close to giving you x. Okay, we could just make a little change. We could change this 4 here to a 3, and if we did, then our result would just be x, and we would see that we have inverse functions. So if instead of x plus 4, we have x plus 3 under the square root, it's inverse to this one. Or we could put minus 4 here and leave the plus 4 here, and that would make the two functions inverse. You're going to see things about inverse functions, and you want to know how to test them. And the test is that f of g of x equals x, and also that g of f of x equals x.